we have looked at the definition of an mth order Markov source. Mth order Markov source was defined as the source which emits symbol wherein the occurrence of each symbol is dependent upon m preceding symbols. We also looked at the definition of an ergodic Markov source, where we said that the probability distribution over the set of states for an ergodic Markov source remains constant. It does not change with time. What we are interested is in calculation of entropy for an mth order Markov source. In order to do this, the first thing that we have to calculate is the probability distribution over the set of states. Let us take an example and find out the procedure to do this. Let me go back to the previous example which we had looked earlier, where I have a second order Markov source and the conditional transition probabilities have been given as shown here. So, this source consists of two binary symbols 0 and 1, and it is in a second order source. Therefore, you have 4 states and the transition probabilities have been given as shown here. For this, we can draw the state diagram very easily, as I have 4 states S1, S2, S3, S4, and the state diagram for this is as follows. We had drawn the same diagram earlier too. So, this is my state diagram for our example under discussion. Now, if it is an ergodic Markov source, then I can find out what is probability of these 4 states based on the conditional symbol probabilities. Let us look at that. Now, for any particular state, if I want to calculate what is the probability of the state, that would be given by this following expression. Probability of being in a particular state Si, given I was in a state Sj, and what is the probability of the state Sj, that is given by Psj, and this is summed over all the values from j equal to 1. In our case, there are 4 states, so you will have 4. In general, it would be q raised to m, where q is the size of the source alphabet and m is the order of the Markov process. So, using this expression, I can find out what is my probability of states. Now, for our specific example, this can be reduced to writing something like this. I can find out what is my probability of S1. Obviously, my probability of S1 is probability of S1 given I was in S1, that is 0.88, and what is the probability of state S1, that is which I am supposed to calculate. I cannot come to S1 state from S2, nor I can come to state S1 from S4. So, all these are 0, whereas I can come to state S1 from S3. So, I get probability of S1 given S3 is 0.5 and probability of S3 itself is indicated here. So, I have 4 simultaneous equations, and if I solve this 4 simultaneous equations, what I get are these values. So, these are the probability distribution of an ergodic second order Markov source. Now, once we have this quantity, we can find out what is the entropy of this same source which is under discussion. Let us look at the calculation of the entropy for such a source. Now, if I want to do that, let us try to develop a general expression for a mth order Markov source. So, we will calculate now entropy of mth order Markov source. So, let us assume that the source was in the state given by Sj1, Sj2 up to Sjm. If the source is in the state given by this, then there are m conditional probabilities, there are q conditional probabilities associated with this state, q because the length of the source alphabet is q. So, let us find out what is the conditional probability of receiving symbol S I given I was in this state will be nothing but probability of S I given Sj1, Sj2, Sj3 up to Sjm. So, when I receive a particular symbol Si given I was in this state, then the amount of uncertainty resolved or the amount of information which I gain on the occurrence of Si in this state will be given by I of, this denotes the self information which I get on the occurrence of Si given I was in state Sj1, Sj2 up to Sjm is nothing but by definition as seen earlier log of 1 by probability of Si given Sj1, Sj2, Sjm. So, this is the amount of information which I get on occurrence of a particular symbol Si. Now, if I average the information which I get when the source in the state given by this, then that would be H of S, Sj1, Sj2 up to Sjm is equal to probability of Si given Sj1, Sj2, Sjm information which I get is this. This is summed over the source alphabet S. So, this is the average amount of information per symbol while we are in state this. Now, this state itself can change. So, if I average this quantity over all the states, then what I will get is the entropy of that mth order Markov source. So, to get the entropy from this quantity, I have to take the average. So, the entropy of the source would be given by probability of being in a particular state, that is given by this multiplied by the average information that I get when I am in that state this quantity is obviously averaged over all the states. So, there are number of states which we can have is given by q raised to m. So, I should sum this quantity for all the states qm states. Now, to denote that summation, I will just use an abbreviation. I will denote this as Sm. So, when I write Sm, it means that I am summing this over different q raised to m states. So, let us try to simplify this quantity. What I will get is Sm this quantity comes from here. So, I can write this as now I can take this summation outside, and if I do that, what I get is h of s is equal to probability of Sj1, Sj2, Sjm, Jm log of now this summation is over this states and also over the source S. So, to denote that in abbreviated form, I will write it as S plus M 1. Okay. So, this can be simplified as this quantity can be simplified as multiplied by log of probability of Si Sj1, Sj2, Sjm. So, this is the final expression which we get for the calculation of an entropy of an mth order Markov source. Let us take an example and try to evaluate this expression to get the feel of what we are doing. So, let us go back to our previous example which we had considered, that is second order Markov source, for which we just calculated the probability of states. So, if I take that example and if I am interested in calculation for that example, this entropy, then in our case m is equal to 2. So, what will happen, this summation will go for over s raised to 3, and this quantity out here will be 2 elements here, there will be 1 element here, and there will be a conditional probability is given there. So, that can be written as, so this is a previous example which I have. Let us try to understand this, what I have written here. So, Sj Sk denotes the particular state. I have 4 states. So, 0 0 0 1 0 1 1 0 1 1, these are the 4 states which I have, and in each state the source can emit either 0 or 1. So, if when it is 0 0 I can emit 0 or it can emit 1. Similarly, when it is state 0 1 it could either emit 0 or 1. So, Sj Sk Si. So, these are the various combinations which I can have in this expression. This is what I am writing. I am supposed to get this expression evaluated. So, to do this I will require the states. So, I have written down all the various combination of Sj Sk Si. I will also require the conditional symbol probabilities. So, conditional symbol probabilities equivalent of this for this problem is given directly from the specification of the problem. This was given to us as a specification of the problem. Probability of Sj Sk is nothing but the probability of a particular state. So, we have 0 0 0 1 1 0 and 1 1. So, this we had just seen how to calculate, and the values we have calculated are given here. Once I have this, I can find out what is probability of Sj Sk Si by simply multiplication of these two. What I will get is these are these values, right? And then you just take these values. I have these values for each of this. I have got 8 values here, I have got 8 values here, just plug them into this, and what I get is 0.81 bit per minute. So, if I have a second order Markov source, then the entropy of that source is given by 0.81 bit per minute. If this source was not a second order Markov source and it was a zero memory source, then we have shown that when the probability of occurrence of the symbols 0 and 1 are equiprobable, then the entropy of that zero memory source turned out to be 1 bit per minute. So, we find that when there is a dependency upon the symbols, even if the source is a binary source, then the entropy of that source is less than a zero memory source. Now let us take some clue from this example and try to discuss it in a more generic fashion. Suppose if I have a source S which is a Markov source, it could be of any order, and this source S will obviously have some source alphabet. Let us assume they are given by S1, S2, and SQ. Now, for this source S1, S2, SQ given by this source alphabet, I can always calculate the probability distribution of the states. Now, given the probability distribution of the states, it is also possible for me to calculate the first order symbol probabilities, correct. That means unconditional probabilities I can find out. What I mean by that, I am interested in finding out what is the probability of P of S1, P of S2 and P of SQ. These are known as unconditional symbol probabilities. Now, let us assume that I can calculate for a moment. Let me assume that I can do this for any Markov source. Now, if I have another source, let me call that another source is S bar. This source S bar also has the same source alphabet, that is S1, S2, SQ, but this source S bar is a zero memory source. So, if it is a zero memory source, then it has got only unconditional probabilities, and let me assume that unconditional probabilities, right, for this source is identical to the one which we have for the source S. So, the unconditional probabilities are also identical and they are given by PS2, PSQ. Now, the question is, what is the relationship between HS and HS bar? Is there some kind of a relationship existing between these two sources? What it means basically that in all respect the source S and S bar are same, source alphabets are same and the unconditional symbol probabilities are same, but the source S emits symbol wherein the occurrence of each symbol is dependent upon the preceding symbol, whereas S bar is a zero memory source. So, is there any kind of relationship between these two? We will very shortly see that I can show that entropy of HS is always less than or equal to entropy of S bar, a very important relationship. Now, to prove this relationship in general for an mth order Markov source is little bit involved. So, what I will do is try to simplify this source S. For our derivation, we will assume that this source S is a first order Markov process. So, for the first order Markov process, we will try to find out another source S bar given by this specification. Now, if we look at the previous example, that is a second order Markov source where we had calculated the probability of the states, then it is also possible for me to go little beyond and calculate the unconditional symbol probabilities. Now, it is not very difficult to show that. Going back to this example which I have out here, I can, if I were interested in finding out what are my unconditional symbol probabilities for this ergodic second order Markov source, then for symbol 0 I can write down as probability of occurrence of 0 would be when? Probability of occurrence of 0 would be when I am in state S1 and I go back in state S1, because if I go from state S1 to S1, it means that 0 has occurred. And what is the probability of occurrence of being in the state S1? So, if I use this kind of information, I can calculate what is the unconditional symbol probability of 0. So, let us do this, write down the expression for the 0 symbol. So, probability of 0 would be probability of going to state S1 when I am in state S1, and what is the probability of the state S1. So, that is 1. Then I can come to this, if I am state S3, then if 0 occurs, I go to S1. So, what is the probability of coming to state S1 from S3 multiplied by probability of S3 itself, plus I have probability from S3 to S2. So, if 0 occurs from S2 to S3. So, if what is the probability of going in state S3 when I am in state S2 multiplied by probability of state S2 itself, and finally, I have probability of, I can come from, when I go from state S4 to S3, that can occur only when 0 occurs. So, probability of S3 given I was in S4, probability of S4 itself. Now, if I know all this value, this is 0.8, this is given out here in the state diagrams, and we have already calculated probability of PS1, PS2, PS3 and PS4. If you plug on all those value out here, you will get probability of 0 to be equal to half. Similarly, you can calculate the probability of 1 is equal to half. So, this we have done, I have shown you how to do it for a simple case of a second order Markov process, but similar procedure can be adopted for a general mth order Markov process. So, what I want to say is that given a Markov source, mth order Markov source, I can always calculate it, the unconditional symbol probabilities. So, let us try to define okay. So, if I have a Markov source S, I will consider just now it is first order, so let me define a mth order Markov source consisting of source symbols S1, S2 and SQ. This is an mth order Markov process, and with each of these symbols I have associated unconditional probabilities These are unconditional probabilities of the symbol, or I can say the first order symbol probabilities. Now, let me define another source S bar, and this S bar is known as the adjoint source of S. This source S bar, which is the adjoint source of S, is a zero memory source with the identical source alphabet S given as S1, S2, SQ and identical first order symbol probabilities PS1, PS2, PSQ. I will denote this in abbreviated form as P1, P2 and PQ. Okay. Now, we are interested in calculation of relationship between HS and HS bar. Now, to calculate this relationship, which we said that would be something of the form HS is always less than or equal to HS bar, I will assume that my source S is a first order Markov source. So, for a first order Markov source, my source alphabet, let me assume, is this. The conditional probabilities which will be involved would be Si given Sj for I j equal to 1, 2 up to q. So, I have the conditional probabilities, I have the source alphabet, and now let us try to calculate what is the entropy for this source. Let us define probability of Sj Si as the joint probability this is a joint probability that the source is in the state specified by Sj and Si occurs. So, I am in the state Sj and then Si occurs. When such a thing happens, this is the probability of Si occurring when I am state Sj, and this is denoted as joint probability. Now, let us try to examine the double summation of the form this double summation is over Sj and Si. So, this I will write it as. Now, we have seen earlier that there is a relationship of the form Qr xi log of yi over xi I equal to 1 to q is always less than or equal to 0, where xi and yi are the set of probabilities. Now, similarly here this joint probabilities Psj Si, if I sum it up over j and I, the value is 1. Similarly, Pj multiplied by Pi, if I sum it over j and I, it is always equal to 1. What it means from this relationship, that this quantity out here is always less than or equal to 0. Now, we also know from the Bayes rule that probability of f j S I is equal to probability of S I given S j multiplied by probability of. If you plug in this expression into this, then I can write as Pi over probability of S I given S j is less than or equal to 0, which I can further simplify as probability of S j S I log of probability of S I given S j will be less than or equal to probability of S j S I log of 1 by Pi. If you look on the right hand side and concentrate on this term, this is nothing but equal to double summation of probability of S j S I log of 1 by Pi. The summation is over I is equal to 1 to q, j is equal to 1 to q, and this summation, that is probability of S j S I j equal to 1 to q, is nothing but probability of S I. So, finally, what I get is I is equal to 1 to q probability of P S I log of 1 by Pi. This quantity is nothing by our definition as entropy of H s bar, and this quantity out here, it is very easy to identify in the light of what we have done earlier today. This is the expression which we derive for entropy of an mth order Markov source. In our case, a source is first order, so this becomes S2, and this expression simplifies to this expression. So, this expression is nothing but entropy of Markov source. So, from this relationship we get as H of S is nothing but less than equal to H of S bar. This we have shown it for a first order Markov source, but this is also valid in general for any order Markov source. Going back to our previous example, H s we got as 0.81 bit per minute, and for the same example we calculated the first order symbol probabilities were P0 half and P1 again half. So, my adjoint source for the example which we considered earlier would be S bar would be nothing but I have a source alphabet consisting of 0 and 1, and my probability of 0 would be the same as my unconditional symbol probabilities for the source S, and that is nothing but equal to half, and probability of 1 again is equal to same identical to this. So, it is a half, and to calculate entropy for this, it is simple. H of S bar is 1 bit per minute. So, what it shows that this expression is valid. This we have shown for our example discussed earlier. Now, to go little further and find out little more in depth about the mth order Markov source, I need to define some few more definitions. With that intention, let us consider a following example. Suppose I carry out an experiment. This experiment consists of tossing of a die and a coin simultaneously. So, when I toss a die and coin simultaneously, and if I am interested in the outcome of this experiment, then I will have two outcomes for this experiment. One is basically the number which I get on the die, and the other is basically either its head or tail. So, I can formulate in many cases experiments which have two outcomes. So, I will say that experiment having two outcomes denoted by, let us say, x and y. So, x and y, this way, which the way I have given here, denotes an experiment. Now, the outcome of this experiment are the values xi and yj. They will be occurring jointly. Xi comes from a sample space, let us denote it as this way, and let us denote yj coming from a sample space x y like this. So, for this experiment xy, I have the elements xi yj belonging to a sample space given by this. In the way I would like to define some kind of information measure to the outcome of this experiment, where the outcomes are not a single events, but they are two events. So, how do I define information measure for such an experiment? It is very simple to do if we follow the following procedure. Now, the number of events which can occur given by xi yj will depend on the size of the sample space x and the sample space y. Let me assume that the size of the sample space x is n elements and the size of the sample space y is m elements. So, totally I will have nm elements. Let me indicate this nm elements given by the joint occurrence of these two events as Z1, Z2 up to Znm. Now, with each of this event xi yj, I will have probability of occurrence given by probability of xi given yj. Now, in the light of our definition of in terms of z, this is nothing but equivalent to probability of z1, probability of z2 and probability of z nm1. So, an experiment which had two outcomes has been reduced to an experiment which consists of single elements given by z1 to znm1 with its probabilities of occurrences. Now, this has been reduced to a one dimensional sample space. Let us call this one dimensional sample space as Z. Now, if I were to find out what is the information associated with this experiment, then going back to our definition, I can define the information measure for this experiment is nothing but given by this simple expression. Where my I goes from 1 to nm. So, this is the information measure associated with this experiment Z. Now, this is going back to our original notation. I can write this as nothing but P of xi yz log of P of xi yz, and my summation will be double summation I equal to 1 So, I have been able to calculate the information measure for this experiment, my original experiment, which was given by this sample space. So, I can use this argument to define my information measure for joint event as x y equal to I is equal to 1 to n, j is equal to 1 to m. So, this is the information measure which I will define for my experiment consisting of two events. So, we have seen that if I have marginal probabilities or just simple first order probabilities or unconditional probabilities, then with marginal probabilities we had associated an information measure, and that was marginal information measure, that is equivalent to the self information which we had defined earlier. Now, we have seen that if I have joint probabilities in the form of P of xi yj, I have joint probabilities, then I can define joint information measure. This is joint information measure. So, the question that arises is that suppose if I have two different experiments x and y, and possibly the outcome of this two different experiments are related in some manner, and the question arises, is it possible for me to define something what is known as conditional information measures because I can always associate conditional probabilities with those two experiments x and y. For let us assume that the elements of this experiment x is xi and the elements of the experiment y are yj, then we have probability of yj given xi. If there is a relationship existing between yj and xi, then I can define my what is probability of yj given xi. If these are given to me, then is it possible for me to calculate it? This is nothing but conditional probabilities. So, if these are conditional probabilities, then based on these conditional probabilities, I can also define what is known as conditional information measure. Let us look into the definition of conditional information measure. To understand this, let us assume that I have two probabilistic experiments x and y, and I am interested in amount of information with regard to y under the condition that outcome xi has already occurred. And then since we have been given conditional probabilities, and also so let us calculate by definition the average information which I will get about the experiment y when xi has occurred would be by definition given as y of xi is nothing but probability of yj given xi log of probability of j given xi, j is equal to 1 to m. Now, by averaging this quantity over all xi, then what I will get is the average amount of information of y given foreknowledge of x. That is very simple. What I have to do is take the average of this quantity. So, average of this quantity is nothing but p of xi h of y of xi I is equal to 1 to m, and if we just write this expression I is equal to 1 to m and substitute this expression out here, we can simplify this very easily to I is equal to 1, m, j is equal to 1, probability of xi yj log of probability of yj given xi. Okay. I have changed my notation from capital P to small p, they are same. Okay. So, this is what I will get. So, this is the amount of average information of y given foreknowledge of x, and this by definition I will call it as h of y given x. Based on this argument, I can also define what is my h of x given y, and that would be simply nothing but p of xi yj log of p of xi given yj, I is equal to 1 to n and j is equal to 1 to n. This is the average amount of information of x given foreknowledge of y. Now, based on all these definitions, we will try to probe a little further into Emmett order Markov source.